owed visitors from Oxford. Andrew's worked on a lot of things in his career, a lot of CD cosmology, looking at anomalies, looking at anisotropic universes. Today he's going to talk to us about one of his other vices, which is looking at, well, the cusp core problem in dwarf galaxies. I first met him when we were about students in Cambridge, but since then he's with a postdoc in Cambridge and now a postdoc in Oxford, and so, well, that's really cool.
Thanks, Richard. It's really great to be here, so thank you very much for coming along to listen. What I'm going to be talking about today is, as Richard said, based around something called the cusp core problem, which, in case there are people here who haven't come across that, I will outline it in a moment. But it's a set of ideas that have evolved really over the last 18 months in collaboration with a number of people, and in particular I wanted to mention Fabio Governato, who's at the University of Washington, Romain Tessier, who's at the University of Zurich, and Jorge Penarrubia, who's about to move to Edinburgh University. And also, of course, all the work that I'll be talking about, although a lot of it is analytic, really comes out of inspiration that comes from running simulations, and those simulations would be completely impossible if it weren't for the careful work of people who write these codes. One of the codes I'll be talking about is Ramses, that's developed by Romain Tessier, but with Fabio Governato, I do some work with the gasoline simulation, which is developed by James Watsby, who's sitting right there, and many other people. And finally, I wanted to mention Steve Grattan, who some of you may know. He does crazy cosmology stuff, but some of the stuff that I'll be showing you came out of discussions that we had over coffees. So, to give you an outline of the talk, it looks something like this. I want to start by talking about a process that I'm going to refer to as melting. I'm not really going to explain why I refer to it as melting right till the end, though. But what I really mean by that is just to discuss how cusps, that is centrally concentrated dark matter, are changed and destroyed by energetic feedback processes, the energy coming from stellar populations, in particular inside galaxies. Then I will go on to talk about some brand new ideas that were on the archive just last week about how these dark matter halos formed in the first place, and how we can begin to start putting together a better understanding of why we seem to have, in the absence of any baryonic effects, a totally universal profile for dark matter. Why does it do one particular thing, regardless, it seems, of, say, the mass of the dark matter halo that you're looking at, or even the spectrum of the fluctuations from which that halo formed? It seems to be remarkably universal, and we've been doing some work with statistical mechanics to give a fresh look at why that universality might be coming about. And that gives us a new way to go back to what was the content of the first part of the talk, which is to go back and look at this cusp destruction process with these statistical mechanical ideas in mind. And the third part of the talk is in fact so new that it's newer than last week. It's certainly not on the archive yet, and is a little bit more speculative than the rest of it, and so I'd be very grateful in particular for any comments on that part. So to begin with just a rough overview of what it is we're talking about, if you run a dark matter only simulation, then you find that the kind of end product of nonlinear collapse are this series of dark matter halos. And these dark matter halos, for at least 2 decades, it's been known that they have this more or less universal form. It's sometimes referred to as a NFW halo, after Navarro, Frank and White, who had a kind of seminal paper looking at the properties of these things. And its basic properties are that in the center of these halos, there's a very high density of dark matter. So this is just plotting the spherically average density of the dark matter as a function of radius. So it's high in the center, it drops towards the outside, and it does that in a pretty predictable way. Roughly speaking, the density drops off as r to the -1 in the center, and as r to the -3 on the outside. And that's been robustly reproduced by a huge number of simulations over the years. and so most people believe that this is the correct answer to the problem of what happens when you allow non-linear structures to form in collisionless dark matter. But the trouble is that when we go and look at the real universe, mounting evidence that nowadays I think we can regard as pretty secure, suggests that observationally, especially in smaller systems, this is not the configuration in which the dark matter is found. So, in particular, if you look at dwarf galaxies, I'm talking incidentally about field dwarf galaxies, not the satellites of the Milky Way, which are slightly more complicated systems. But if you go and look at dwarfs out in the field, you can measure their properties quite nicely. You can measure things like rotation curves from a neutral hydrogen gas. And this gives you a pretty good measure of what the gravitational field is. And through techniques people have developed, you can subtract the contribution of the baryons, which is not too dominant, and reproduce from that what the density of the dark matter is. And it now seems like, interior to about a kiloparsec, the observations in dwarf galaxies just don't agree with the simulated results. They have something more like a dark matter core. That name suggests that they have exactly constant density in the center. That's perhaps not the case, but it's certainly a shallower power law, if you like, than is predicted by the dark matter-only simulations. So we can go beyond this sort of Fisher-Price picture and show you some actual observations. This is a compilation from the literature. It was put together by Se-Hyun Oh from the things team and adds a few more dots, which are the ones in colour. But what it's showing is the log slope of the inferred density of the dark matter as a function of the innermost radius where that can be measured. So on this plot, one of these NFW universal halos would follow something like this line, and in the centre it would asymptote to around about -1. Whereas the observations, although you can argue with individual observations in some cases, as a whole, they seem to lie pretty robustly above that prediction. That translates into a shallower density profile in the centre of these things. So it seems like for dwarf galaxies, the situation is becoming increasingly clear that the observations don't agree with that simple theory. And now, perhaps, the new observational frontier is at the other end of the mass scale. There was this nice series of papers last month, came out by Andy Newman and his collaborators, trying to do a similar reconstruction of what the dark matter density was in the center of clusters with a BCG in the center. And they use a combination of lensing and kinematic information to try and reconstruct the density profile. And here what they're plotting is their posterior probability for individual halos. So each of these thin lines corresponds to one of their observational sample. And it's the probability density for that individual having a particular inner slope. So if these things were genuinely NFW, then they ought to have a value of 1. And as you can see, there are a number which are incompatible with 1. And more particularly, if you take a combination of all of these and put together the total posterior probability given all of these clusters, you get something which quite robustly excludes the NFW limiting value. Now, these observations are not without controversy, but nonetheless, I think it seems like they are heading in the direction of finding a similar discrepancy to the one that we're now fairly secure about in the dwarf galaxies. Oh, sorry. So the x-axis is measuring the inner slope. So it's, if you imagine it, it's like fitting a power law to the density law in the middle of the cluster. And the y-axis is just the probability density. So this thing is, as you go to the left, it's getting shallower and shallower. And you can see that the combined probability density peaks at something a lot shallower than what would be predicted by the simplest arguments.
Why are observations being dwarf galaxies?
Yeah, well, so the dwarf galaxies are a particularly nice example because they seem to be quite simple systems in the sense that their baryons form just more or less just a disk. You can think of it just as a baryonic disk plus a dark matter halo, and that makes it quite easy to do the kinematical decomposition and subtract out the effect of baryons. As you go into bigger galaxies, that becomes harder because they have complicated things like halos and spheroid bulges and things at the center. And then when you go up to the cluster scale, you're dealing with something slightly different because you're using a combination of strong and weak lensing and stellar kinematics. So the constraints look quite different in detail.
So all those three methods for the clusters give the same result? Or
no, you have to use them together, which is why these things get a bit controversial, because you can imagine you might be biasing things. But for what it's worth, as far as I can tell, although I'm no expert on these observations by any means, as far as I can tell, these guys seem to have done a pretty careful job of it. So, okay, so I got interested in this problem probably about 2 years ago now, when Fabio Governato, who I previously collaborated with, but at this time I was working on something quite different. So Fabio and his group at the time put out this Nature letter saying that they'd run a simulation of a dwarf galaxy where they did two things which were of interest to observers. First of all, they were bulgeless. So typical dwarf galaxies don't have a stellar bulge, and that's something that simulations don't tend to reproduce. Normally the simulations end up with a pronounced stellar bulge in contradiction to the observations. But also, they were also forming dark matter cores as well. And the question was, why are these simulations doing both of these things in contrast to the previous simulations that this group and other groups had run? And what was new about this paper was that it was able to do both of these things in a fully cosmological environment that ran all the way to redshift naught. Now, a kind of qualitative shift in what was going to be observed in cosmological simulations of galaxy formation had been anticipated by a number of people. This is a paper from 2008 by Severino and Klippin, which makes a fairly clear point of the following. It says that as we go to higher resolution, that was, in fact, the main driver of these changes, simply going to higher resolution. As we go to higher resolution, we should start to see qualitatively different effects of supernova feedback on the interstellar medium. And in particular, these guys argued that you would naturally begin to see outflows of gas. And the argument goes something like this. If you imagine a low resolution simulation, then if you're resolving some gas disk in your galaxy, and that has some density that varies as a function of position. And you need to know, in that simulation, where do you form the stars, because that's where the energy injection from supernova is going to go in. And all you can do in simulations, because you're never going to resolve actual stars forming, all you do, to put it simply, is you put some density cutting, and you say, okay, stars are going to form at high densities, but we can't resolve the actual densities that stars form at, so we just say, well, the highest density gas in this simulation is going to be the gas that spawns the stars. So you try and work out, well, what's the highest density I resolve reasonably reliably, and up until, say, the late 2000s, typically people would go for about 0.1 per centimeter cubed, which is around the density of the warm interstellar medium. Now, what changes as you go to high resolution is that if you get physics right, you're able to cool to much colder, denser clouds. And so on top of this large-scale fluctuations in density that you might have in a disk, you also get small-scale fluctuations in density where you get very local, very dense clumps. And at that point, it no longer makes sense to associate the star formation with all of these clumps. You still know you're not actually resolving where the stars form, so you want to associate the star formation with the stuff that's got to the densest thing that you can resolve. So you actually change the star formation threshold up to maybe something like 100 per centimeter cubed instead, so around about the densities where you might start to see molecular clouds. And that means that the stars form in much tighter clusters, and they inject their energy into much smaller regions, And the result is that those regions get a very high energy density, and they're massively overpressurized compared to their surroundings, and they literally explode out of the interstellar medium and launch galactic winds without ever having to put the galactic winds in by hand. So instead of actually having to say, okay, we must have galactic winds in our simulation, somehow they come naturally if you inject the energy into these very dense little clusters that form stars. So that's the picture that these guys put together, and it's a picture that's been seen in a lot of work since. So here is a simulation rather similar to the Governato 2010 one that I was just showing you the paper for. This is a simulation that I run using this gasoline code, and is, as you see the structure develop, this green stuff is dark matter. As you see it form structure, you also see gas, which is coloured by temperature, exploding out of these little forming galaxies. And it really does pump out very fast, and you only see this when you have this high threshold star formation. So this qualitative shift from basically no outflows to really quite energetic outflows is behind everything that changes in these simulations. Now, the first question was, why are these things not forming stellar bulges anymore? And Chris Brook put out a paper explaining this quite nicely. I've just got one slide on this to show you. All he did was he measured the angular momentum of the gas that was being thrown out of these galaxies. And that's plotted as a function of time as these white dots here. And compared it to the angular momentum of the gas that remains bound at any time, and that's this yellow line here. So he found that the gas being pumped out systematically has lower angular momentum than the gas that the system can hold on to. And the result of that is that you remove a lot of the low angular momentum baryons, and it's those baryons out of which you would form the stellar bulge. So it seems like this is why you don't get a stellar bulge. But the question of why these outflows gives rise to dark matter cores is a little harder to unpick, because actually there's a rich existing literature on this subject, which I just want to try and give you my interpretation of in one slide. It's rich. A lot of people have written a lot of stuff about this, but it's also quite confusing because there's an awful lot of it, and some of it at first sight seems to be contradicting other parts of it. So I'll just try and take you through what I think are the important developments. And it was realized right in the early days of being able to run these cosmological simulations that the gas would have an important impact on the structures that were finally formed. And so here are two early papers who both realized that there were two possible important things to take into account. The first is something called adiabatic contraction. So that's simply that if you smoothly pour lots of gas into a dark matter halo, it steepens up the potential in the center of that halo. And then dark matter particles that are orbiting around contract in response to that. But they're just pulled in, if you like, as the potential steepens up. So that's one effect. But of course, that makes things worse. That means that the dark matter gets more centrally concentrated rather than less centrally concentrated, which is what we want to agree with the observations and what we're seeing in the new simulations. But these people also pointed out that if you remove the gas again, of course, you reverse the effect. So if you imagine that you pour lots of gas in, but then somehow it's removed again, then you go back to what you started with, and you can show that analytically, in fact, that if you pour gas in slowly and remove it again slowly, you end up with exactly the same dark matter profile as you started with. And both of these papers went a step further and did some numerical experiments of what would happen if you pour the gas in slowly and then remove it quickly. At this time, there was no way to do that analytically, so they just did a numerical experiment where they allowed some dense stuff to grow at the center and then very quickly removed it all. And they found that if you did that and you did it with a large mass compared to the mass of the full halo, then you could actually overcompensate, if you like. So first of all, you steepen it up, but then when you remove these baryons, then the central density profile becomes shallower. So that kind of works in the right direction. But the trouble is that if you want it to do anything useful, you need to use more than the cosmic fraction of baryons, in fact. And this was underlined by some work by Oleg Nedin in 2002, where a sort of a semi-analytic model of this whole process was put together, and they really underlined that you needed to use more baryons than you even had, and then you needed to remove all of them. And so it seemed like this process just couldn't actually do anything in the real universe.
But the suddenness is also an issue, particularly when you move it
Yeah.
dynamical time.
Yeah, that's absolutely true.
It has to be incredible, one way, not just several dynamical times.
It has to be, absolutely, it has to be less than one dynamical time. And in a moment we'll see how that actually can happen. But agreed, it seemed kind of implausible at this time. You can remove all the gas in less than one dynamical time. It seems totally crazy. But on the other hand, Justin Reed came along in 2005 and kind of gave a bit of hope to this picture by pointing out that all of these previous works had assumed you needed to do everything in one episode. And what Justin showed is that if you accrete lots of baryons and then you still need to remove them all suddenly, but then you re-accrete them and remove them all suddenly again, then somehow there's a cumulative effect. So you don't any longer need more than the cosmic baryon fraction to be able to do something interesting. Still, it seems like what you're doing is incredibly violent compared to anything that would seem plausible, but it's slightly more hopeful. Now, in parallel with all of this work, there was a sort of separate thread in the literature looking at dynamical friction, and this idea was sort of originated by Ami and Elzant. And the idea is that if you have very dense clumps spiraling in to some halo, then those clumps have a gravitational effect, which is called dynamical friction, which transfers energy from the clump that's coming in into the distribution of dark matter particles. And again, you can do numerical experiments where this turns a cusp into a core by injecting energy into the center. The trouble is with this whole picture is that certainly at the dwarf galaxy scale, it's very hard to see how you can have these dense clumps being produced cosmologically and dropping them in sufficient numbers. No consistent numerical simulation has ever been able to do this because you need lots of very tiny objects which have a lot of baryons in them, very, very dense baryons. You never get to sufficient densities with dark matter alone, so this is always a baryonic effect. You need tiny little dark matter halos with very dense baryons at the center, and you need a lot of them. And it seems very hard to reconcile that with any of our current pictures of how structure formation proceeds, at least for dwarf galaxies. I mean, I think there is more of an argument to be had up perhaps at the cluster end, where, relatively speaking, these things are then quite large galaxies that fall in. Maybe you can do that. But nonetheless, it doesn't seem to really answer the question for the dwarf galaxies. So we're almost there in the literature review. There are just two more papers, or maybe three actually, that I want to mention. In the middle of all this, Weinberg and Katz had a classic paper showing that if you form a strong bar during structure formation, then this is, at least in theory, able to transfer energy from the baryons into the dark matter. So then you don't need to actually remove the baryons. You can just have some kind of strong feature in the baryons that, again, through something a bit like dynamical friction, it's transferring energy into the dark matter distribution. But perhaps a sort of synthesis of lots of these ideas came in a couple of papers by Mushenko, who's one of James Wadsworth's students, pointing out that you could kind of combine, in my picture, what's going on is you're combining a lot of these different ideas together. So if you imagine you have some dense baryonic clumps in your disk of the forming galaxy, and these are constantly being pushed around by supernovae, then they can transfer their energy, so they have some kinetic energy which can be transferred into the dark matter through some kind of coupling process, and that gives you not only the mechanism for the coupling, but also the source of the energy comes. So the source of the energy comes from the supernova explosions, but the coupling is more like the ideas maybe of Weinberg and Katz, or more like a sort of dynamical friction picture where the coupling is much more gentle. So that is my summary of where the literature was at this point. But what we wanted to do was to put together a model where we could really say quantitatively what was happening in these simulations. And a lot of the problems with the second half of this literature was there are no kind of toy models to actually work out quantitatively what should happen in these cases. So we wanted to go ahead and create a toy model, which is what I'm going to present to you now. And it has a lot of stuff in common with a lot of the papers I've just spoken about, but I'll just go ahead and present it as we discovered it, if you like. And so we started by opening up the simulation and just looking at what the gas mass interior to a certain radius was as a function of time in these simulations. So if I plot the gas mass interior to, say, 200 parsecs as a function of time, it looks something like this. And the first thing you notice is that it's changing by orders of magnitude. And it's changing on very short time scales, less than a dynamical time scale. In fact, the dynamical time scale in this thing might be something like 100 megayears in the center. And these masses are changing more rapidly than that. And moreover, they're changing in a coherent way. So if you look at the mass interior to 500 parsecs, that also changes, and when the mass at 500 parsecs dips, so the mass at 200 parsecs also dips. So all the way out to about a kiloparsec, you can see these effects, although as you go further and further out, they become less and less pronounced. So what you kind of expect is if you open up the simulation at this point, where the mass is very low, then something dramatic must have happened. And in fact, that is what you see. So if you take a slice of gas through the midplane at this point, you see a big hole has opened up in the center of your galaxy. And you can verify that the reason that hole has opened up is because you have some very high temperature gas in the middle. It's been heated up by supernovae, and it's opened up this big coherent feature in the center of the galaxy.
How many massive stars are you tracking?
In one of the bursts, that's a good question. I don't have that number off the top of my head. I'm guessing it's about 10 to the 6 solar masses in a single burst.
So you are moving 10 to the 6 solar masses in gas?
You are moving around 10 to the 6 solar masses in gas, and you've formed around 10 to the 6 solar masses in stars. These numbers are about the same. I mean, the important point is that you change the amount of gas by about an order of magnitude. Now, right in the center, the potential is actually dominated in the central couple of hundred parsecs by the gas. It's dense enough at the times when it's dense that the potential itself is dominated by the gas. And then the gas disappears and the potential flattens out to the point where you only see the dark matter potential. So what this picture is really telling you is that the potential in the center of the galaxy is definitely changing on less than a dynamical timescale. What's slightly different about this from any of these really extreme pictures that have been put forward in the late 90s is that not all that gas leaves the galaxy, and in fact you only shift it out maybe to a kiloparsec or a few kiloparsecs. And then a lot of it cools and comes back, although some of it does leave in an outflow, as I showed you earlier on. But that doesn't matter for the picture I'm about to show you. What matters is that the potential changes in that small central section on less than a dynamical timescale.
Well, the most obvious interpretation of this is that I have some piece of this inner disk, which is undergoing bursts of star formation, and the specific energy released by star formation is large enough compared with the binding energy of the gas to remove the remaining stuff. Otherwise, I don't understand how you can get a coordinated burst occurring on less than the dynamical time.
So yeah, it's always one burst. It's not like two different things in completely different parts of the disk. You can check it is just one burst of star formation in one place that triggers these things.
And
so
do you see some off-centering?
Yes. These things are not always perfectly centered, but unfortunately for the purposes of my model, I'm going to assume they are. Okay, so the idea of this model is just to try and model that in a simple way. So we start with a harmonic oscillator. If you imagine what happens if the harmonic oscillator potential flattens out, so that's like removing some gas, but you do this slowly. If you remove the gas slowly compared to the dynamical time and then put it back nice and slowly, then you get the result that people knew already, which is the adiabatic result. The final energy of any particular orbit in this potential is the same as the energy you started off with. That's no surprise. But what we did that was different is we tried to write down expressions that would be valid in the impulsive limit. So if you take this example again, but you instantaneously flatten out potential and then slowly allow the gas to come back so the potential slowly steepens up again, then you get a qualitatively different effect. And it turns out you can do this analytically by doing a sort of averaging process over all phases of the particle at the point where the gas left, and get an analytic expression for what the energy is expected to be at the end of this process in terms of its initial energy and the ratio of the depths of the potential wells. And you can take my word for it and check afterwards that the thing on the right-hand side here is always greater than 1. So you always expect to gain energy if you have one of these sudden changes followed by an adiabatic return of the gas, which steepens up the potential again. What perhaps is slightly more surprising is, in fact, even if you allow all your changes to be sudden, you still get the same effect. So if I suddenly flatten out potential, so the gas suddenly goes, and then for some reason, any reason is swept back in on a pressure wave, for instance, the gas suddenly comes back, things suddenly steepen up again. In that case as well, you can do this averaging, and again, this thing on the right-hand side is greater than 1. You always expect to gain energy through this process.
So you average, you're averaging over all the phases at which this could have happened.
That's correct.
Right? Because I can think of phases where
yes, absolutely. So there are certain phases where you lose energy, but you make the assumption that the timing of the supernovae is not timed to any particular phase of your dark matter particle.
And plus you have many dark matter.
Yeah, exactly. They somehow sample the whole space. That's right.
Why is it not time symmetric?
Aha, that's a very good question, and I spent a lot of time worrying about that. Because it sounds like it's time symmetric, right? Because you open it up and then you close it up. It's to do with what you mean by the phase averaging, and in particular, you're at a random phase of the orbit before the sudden change happens, but immediately afterwards, that actually puts you at a special phase. So if you imagine you're in a steep potential, for instance, and then it suddenly becomes flat, you're now at a special phase because you're preferentially right in the center, whereas your orbit's going to take you out all the way over here, a long way. So immediately after one of these transitions, you're at a special phase. So the phase averaging introduces a time asymmetry in all of these changes. Okay.
While we're asking, sorry.
Yeah.
What is the escape energy from the galaxy for reference compared with the binding energy of the central piece that's undergoing these oscillations?
Oh, it's quite large, so not many of these particles typically actually escape. So you can formalize this and move away from just this toy harmonic oscillator case by using something called the radial action. I don't want to spend too much time on this. Some of you will no doubt know a lot about it, but one way you can think about what this quantity is it's like an angular momentum almost. It's got the same dimensions as angular momentum, but it's describing, instead of the angular part of the orbit, it's describing the radial part of the orbit. So somehow the angular momentum and the radial action are two very significant coordinates that you can use to describe your phase space. And it turns out everything comes out very naturally in terms of describing things in terms of their radial action rather than in terms of their energy. Because it's a standard result that if the potential changes slowly, then the radial action as well as the angular momentum are conserved exactly for any given particle if the potential changes slowly. But what was new about this work is that we pointed out that in the case of rapid changes, you can still write down what happens to the average of the radial action. And in fact, it turns out that the average of the radial action is left constant even during rapid changes. So I'm not showing you a derivation of that now because it's a little involved, but it is in the paper. if you want to go and see it, and a different version of it is in the most recent paper on the archive a few days ago. So you can use the idea of these sort of average conservation, replacing conservation for an individual particle, to derive what happens on average. And that's just the same as the phase averaging we were talking about for the harmonic oscillator.
What's the difference between the average and the total? The total is conserved.
Yeah. So I use those interchangeably because you imagine that the average for an individual particle is the same as the total for the ensemble of particles in the way it behaves. So what we found is if you use that idea to generate some equations for how sudden changes in potential affect orbits, you can just calculate how does the mean radius of an orbit change as a function of time, given the actual time series of potentials from the simulation. And if you start something on a circular orbit at 100 parsecs, for instance, it migrates outwards like this. And you can compare that to what would have happened if we'd assumed things were exactly adiabatic. And using the adiabatic equations, you get a different result. You get temporary changes in radius, but they're not permanent because we know that the gas cools back down, the gas comes back, the potential comes back to what it was. So the irreversible aspect of this only comes out when you know that the changes are sudden and not slow. So you can do this for a whole ensemble of particles starting at different radii, and you find that they migrate outwards. Roughly speaking, if they start interior to about 500 parsecs, they migrate outwards outside that radius for the potential changes in our simulations, but the particles are left pretty much unchanged.
How does this conserve radioactive if you move fraction of particle outward?
Yeah, well, so the trouble is that the radial action is conserved is conserved in one individual jump, but the averaging procedure means something different on each jump that you do. So it gets a little bit subtle when you have to. So you derive an equation for the shift from that, and then you apply it to the time series of potentials. Sorry, the analytics of this get quite involved. So I'm sorry if that doesn't completely answer your question, but we can look at the analytics afterwards.
If it's conserved, does that mean something else has the action
No, because the averaging that you're doing is over a different population on each jump. Okay? Okay, so you can then take this ensemble of particles and work out what happens to a halo profile. And you find that, in fact, you can work out how slope changes as a function of time. And because all these particles are migrating outwards, you end up with something that is compatible with the observations. It has a dark matter core rather than a dark matter cusp, which is what the ensemble of particles started off having. And this white line has been derived by pushing it through these equations based on the phase averaging idea. And the orange line is what happens in the actual simulations. These things seem to agree pretty nicely. So we think that this toy model describes pretty well what's happening in these simulations. So the question then becomes slightly different. It becomes, well, if this is what happens in the simulations, that's fine, but that doesn't tell you that that's what happens in the real universe, of course, because these simulations have a particular hydrodynamical solution, they have particular behavior of the way the star formation works. And so the question moves on to whether you can really get these highly bursty star formation episodes that really clear out a large fraction of the gas from a central kiloparsec or so of the galaxy. And that's a question which I can't give you a straight answer to today, and it's going to take some time to sort out. And what's most important, of course, is that we know there are completely different mechanisms that could have led to cores in nature. And in particular, here's a snapshot from a recent paper looking at self-interacting dark matter. So you could have some kind of particle physics process that leads to the formation of these cores. And maybe this star formation process never happened, and actually when we see these cores, we are seeing the imprint of something that's genuinely telling us about the nature of dark matter rather than just astrophysics.
I thought white matter claimed that it goes deeper when you interact.
Oh, so there is a timescale thing here. So when you evolve for long enough, you get an instability, and then it gets steeper. But there's an intermediate time where it's actually shallower. That's what comes out of this paper anyway, and I've seen it in other papers as well.
What are the concentration parameters of these low mass scales? I don't remember.
For the NFW fits, the concentration parameters are 10 maybe.
So it goes up towards lower.
Yes, that's right. Yeah. So the really big question is, can we tell the difference between some exotic particle physics models where you generate these cores and just the slightly more boring, perhaps, and from one perspective, effects of baryons? And it would be nice if we could do that. I want to give you a couple of things that we might go after to do that. I think one of the clearest things we can go after is the scalings. How do the properties of these cores observationally change as a function of, say, the stellar mass of a galaxy? And this is a snapshot from a paper which we had about this earlier in the year, showing that in the simulations, you need a reasonably large stellar mass, maybe 10 to the 7 and above, in order to land up here, which is where you have cores. And if you have less than 10 to the 7 solar masses in stars, you land down here on the line, which is just the normal dark matter result. So if you can measure cores in really faint things, and unfortunately that limit seems to be slightly fainter than, say, Fornax and Sculptor, which is where you have current data that seems to be suggesting there is a core. But if you could go just slightly fainter with the dwarf spheroidals, then you might start to learn something. And this seems like it could be a sort of fundamental limit in terms of how much energy is available to you from the baryonic populations. Another thing you could do is go after the stellar dynamics. So the stellar orbits are collisionless in the same way that the dark matter orbits are, so they should be subject to the same processes. So in a paper with Romain Tessier, we had a quick look at this, and in fact, when you have no feedback, this simulation forms quite a nice, thin, rotationally supported disk, whereas when the bursty feedback is on and you form a core, you also form a much more puffed up stellar population, which is largely pressure supported, which perhaps is in encouraging agreement, actually, with what you see in real isolated dwarf galaxies.
Each of these oscillations, you were talking about half the mass in stars, half the mass in gas, but that sounds like there's a strong damping effect in star formation on these oscillations.
Yeah, so I guess once you've formed enough stars, it becomes harder in the sense that you have some stars there that sit in the potential and stop it from getting too shallow.
But do you really, on each bounce, turn half the mass of the gas in stars?
No. So I was talking about the total gas mass that's involved in the two, so the total mass that you form in stars compared to the total amount of gas that's heated up by that process. But that's not half the gas mass that's in the galaxy at that time. Something else you might go after is outflows. Observers are good at measuring outflows from galaxies, although typically in brighter galaxies. But you might want to try and match the properties of the outflows that are observed with the outflows that come out of the simulated galaxies. So those are some observational prospects for going after whether this is really what's going on in the real universe. But I wanted to move on to something different, which is the thing that was on the archive just a couple of weeks ago, and quickly take you through that, which comes back to this question of dark matter on its own. Let's forget about baryons. Let's just look at the dark matter only simulations. And what people have known for a long time is that if you run simulations, regardless of the detailed initial conditions, you get these NFW halos. And so here are 3 simulations we ran for the purpose of this project. Very different masses, but if you measure their properties in terms of their spherical average density, for instance, they look very similar. They're both well fitted by one of these NFW profiles. And the question is why? Now, the field of physics that tends to be good at explaining why the final state of things is insensitive to the initial state of things is called statistical mechanics, and it works really well for explaining why thermodynamics works. That's what Boltzmann did, essentially derive thermodynamics from statistical mechanical ideas. And the whole program of statistical mechanics is about maximizing something called the entropy. So in some sense, that's a measure of how randomly distributed particles are in phase space, subject to fixing things that you know about the system. And for most cases, all you really know about a system is what its total energy is. And this gives you normal thermodynamics, where the distribution function goes as e to the minus b to e. But this expression is also the expression written down by Donald Lynden-Bell in 1967. It looks absolutely identical to what you get from normal statistical mechanics, but in Lynden-Bell's case, this energy includes not only the velocity of the particles, but also a potential energy term. And his idea is that the process of structure formation in the nonlinear case is a process whereby fluctuations in the potential allow energy to be transferred between particles, even though they can't have direct collisions, which is how we would normally expect in normal statistical mechanics energy to be transferred. In Donald Lynden-Bell's case, the energy is transferred by large-scale fluctuations in the potential. And somehow this redistributes things so that they can find the maximum entropy state subject to fixed energy. Now, the problem with that is that, well, I guess the simplest problem with that is it just doesn't give you the right answer. It doesn't tell you what you actually get from the numerical simulations when you do this experiment numerically. However, if we go back to some of the ideas earlier, I was saying that these actions are known to be conserved when the potential changes slowly. But what we have now is that on average, if you average over the whole population, then any changes of potential conserve these things on average, or if you like, on the sum over the whole population. And so as a result, you can argue that instead of just maximizing the entropy subject to fixed energy, you should also be fixing these things. Now, it's a little bit subtle because these things are only conserved when phase mixing is good, so they're actually only conserved in the latter part of the evolution of the halo towards equilibrium. But nonetheless, we've checked this both analytically and numerically, and it seems to work that these things, especially as the thing starts to settle down, as a halo starts to settle down, these things really are conserved on average, while the individual particles change their values at, say, the radial action. The average radial action for the halo does not change. So you can say, well, what happens then if we ask to maximize this entropy or uncertainty subject to fixing all of these things as well? And you get something that looks very similar. The maths is pretty straightforward. You just chain on extra Lagrange multipliers, beta r, beta j, beta z, multiplying these properties of the particles. And so you can then go and test that idea against what you actually get out of numerical simulations. So for instance, if you measure the distribution of these radial actions in a dark matter only simulation, that's just a histogram of the values of the radial actions in one of these dark matter only simulations. If you compare that to what would have been predicted by the Lynden-Bell expression, it looks very wrong. But if you introduce this extra constraint and use the newly constrained idea of finite relaxation, then you actually get a pretty good fit. Except maybe at the end, but that's only to 0.1% of the mass. This is a log plot, so the mass involved in this is pretty tiny, and we think this is probably just particles falling in which are out of equilibrium with the rest of the halo. So that's one view of the phase space. You can look at a different projection and do a histogram of, well, what's the scalar angular momentum of all the particles in this simulation. Again, you can plot on what would be expected if you just wrote down e to the minus b to e, like Donald Lynden-Bell, and it doesn't fit too well. And you can then write down what you would expect to see with these extra identified constraints. And again, it seems to fit a lot better. I mean, the fluctuations away from the new solution are more noticeable in this case, but they're always around 10%. And we have good reason to think these correspond to the effects of substructure, and we don't need to worry about them too much. There is, however, one problem with this picture. I mean, we got really excited when we saw this because it seems like you've predicted the phase space distribution of your dark matter halo pretty well. But there is one discrepancy which seems to be actually quite significant. And that's highlighted when you zoom in on the very left-hand corner of this plot. In particular, the predicted distribution of angular momenta for the orbits, this orange line here, quite significantly undershoots how many particles you actually find at this low angular momentum end. So if I just put that to one side, so just keep that in mind, we can ask one more question of this maximum entropy argument, which is, can it reconstruct the density profiles, just the real space density profiles, which after all is the thing that most people care about. So here's the density profile for the measured from the simulation. From the full idea of finite relaxation, you'd expect to see something like 1 over r squared. And then if you plot on what you predict from the constrained finite relaxation picture, it matches well on the outside. So it really does do pretty well out here, but it does a lousy job in the center.
But three more parameters to fit that. Right?
Sorry?
But three parameters makes that curve.
Yeah, you can't make any curve you want. In fact, so you can fiddle with these parameters, and you always get this type of curve. We can talk about that afterwards, but in principle, these parameters, of course, you are determined just by the total amount of these things you have, by the total amount of radial action and angular momentum energy that you have. And that just determines the Lagrange multipliers, and then that is it. So it all comes from physics in the end. It's not like just writing down a functional form out of nowhere. You miss the cusp, basically. You get this very wrong. Now, I should point out that's only about 3% of the mass in here. It's because this is a log-log plot, you really exaggerate what's going on up here. And 97% of the mass is exterior to this point, actually. And there you do vastly better in getting the radial density distribution than you did previously. But nonetheless, this is clearly a failure. So if we go back to the question of angular momenta, it turns out that this discrepancy here, if you measure the difference between these two curves, is also around 3% of the mass. And it is actually no coincidence at all. It's exactly the low angular momentum particles that sit at the center of the halo and are messing this up for you. So what's gone wrong? Well, what we think has gone wrong is that there is a large body of the literature pointing out that cusps, the central part of halos, form very early on. And this is just one way of looking at the fact that they have very short dynamical timescales. In fact, so if you look at what particles are doing in the very center of these halos, they're whizzing around really fast compared to the dynamical timescale at the virial radius. And that's reflected also, so if you look at how these things form cosmologically, then this is a result from the Aquarius simulation, showing that the material interior to, say, a kiloparsec or even 10 kiloparsecs fell in between these redshifts. So in this particular case, in between redshift 35 and 6, most of the material is already there in the center of the halo. And in this case, it's not quite so extreme, but it's still early times between redshift 6 and 3. So that's sort of two ways to think about two sides of the same coin, that these things come to their equilibrium very early, and equivalently, they have very short dynamical timescales. And that means that right in the center, when you build up the rest of the halo later on, it just doesn't care. It reacts adiabatically to whatever you do to it. And so probably the right way to think about this is that as well as these extra constraints we've identified on how particles can redistribute their energy, which comes from these arguments involving the action, there's also a constraint that tells you about timescales. And the fact that you form the center early and it has short dynamical timescales means it's hard to equilibrize things between the center and the outside.
So presumably this is easily testable by changing the power spectrum.
No. So this is the problem. It becomes a bit subtle because even if you do monolithic collapse, before you get to the point at which things start to equilibrize, you already segregate your population, in fact. So I played a bit with this. This is not published yet, but the population segregates very early on in a regime that's a long way away from phase mixing, so none of the arguments I've been talking about apply. And once it's segregated and things start to get towards phase mixing, these values are locked in, and there's already some gradient across the whole halo. So even for monolithic collapse, you also get.
So that is sort of what Dalal and Chuckwick and so on.
Yeah. So there are, as I say, there's a large literature of people looking at this, and a common theme is, look, the cusp has its own mind, it does its own thing, and I think that's what's being reflected here. So let me just say one more thing about this, because I know I've got to wrap up. You can do a really crude modeling of this by saying, okay, let's just allow the center to have its own equilibrium. Let's imagine it's a two-stage process, although obviously the reality is more subtle than that. Imagine it's a two-stage process, and so you get the parameters for the center based on their total actions and so on, and then you separately get the actions for the outside. That leads you to detect a second population, which has distribution of angular momentum looking like this, which corresponds to the cusp. And together, these things do describe the angular momentum distribution pretty well. And unsurprisingly, once you get the angular momentum distribution correct, you also get the density distribution essentially correct. So it seems like a combination of this constraining of the transfer of energy in the halo based on this action argument, and an argument based on different timescales within the halo, can get you an explanation for why these things look like they do.
So when you do this separation into two populations, how many free parameters do you have or do you get?
Well, so it depends how you want to start counting free parameters, but on the face of it, if you want to be really negative about this, it looks like you've got 8 free parameters. And so then you go, okay, yeah, you can fit anything with 8 free parameters. But it's not, that's not quite true, because the functional form is actually quite constraining in what you can fit. And moreover, you can, something that we didn't emphasize in the paper, you can derive the parameters. Instead of actually doing a fitting to the phase space, you can just take out these single numbers, which are the total action available in each population. And that just gives you the Lagrange multipliers like that. So the situation is slightly more subtle than just counting free parameters, I guess. I might have 1 minute to say. I think
so. We've had plenty of questions.
Okay. So because there's something absolutely brand new that just came up last week that I'm really excited about. So we're kind of disappointed, of course, that we don't just have one argument that tells you you have the NFW halo. You need a sort of combination of 2 arguments. Maybe you'll be able to put all of this and package it up into one analytic framework. We still hope we might be able to do that, but at the moment you do need a combination of our arguments and other people's timescale arguments. But what I promised to tell you is why I'm now referring to this core formation as melting, and there's a very good reason to think about it like that. If you look at the angular momentum in the dwarf, in the dark matter only simulation, and you write down the maximum entropy solution, just a simple maximum entropy solution, and it has no cusp, then you get reasonable fit at large angular momenta, but as before, if you look at the low angular momentum end, the dark matter only simulation has more low angular momentum particles than the maximum entropy solution would lead you to expect. But if you go into the simulation which has baryons, which has generated the core, you find that the distribution of particles once the core is formed is in much better agreement with the maximum entropy solution. And in fact, bizarrely, this is the only place it changes. It's only right at this very low angular momentum end that you see this change. If you zoom back out, then these are the 2 distributions. They look pretty much identical when you look at the large angular momentum end. And of course, perhaps this is no surprise, when you have relaxation, full relaxation, then we already showed you get density profile with the core. You need something extra to have the cusp. So the picture that seems to be coming out of this is that when you switch on these processes that change the potential on very short timescales, what it actually does is it unfreezes the cusp, it allows that population to interact with the rest of the halo, because suddenly you have things that are coupling processes on different timescales. And then you can go and test this explicitly. We haven't had time to do it yet, but the prediction that this would make would be that whatever your baryonic processes are, as long as they involve perturbing the potential on short timescales, it doesn't matter what perturbations you do to the potential, it should always asymptote towards this relaxed state with a core in it. And that would mean there would be a kind of universal dark matter core that forms when you have any of these baryonic processes in action. Okay, so that is the end of what I wanted to say. Just very quickly in summary, so we have this mechanism that is capable of reshaping dark matter. We have a quantitative model that allows you to go and check whether this is what's happening in a given simulation. So the real question moves on to whether real galaxies actually do these highly bursty modes of injecting energy, which are key to getting this result. You then have put together a kind of quantitative model of constraints on violent relaxation, which gets you a huge factor closer to describing the phase space of simulated dark matter halos. But on the other hand, it has some limitations. It needs extra arguments to explain why there's a cusp in the center of the halo. And finally, right now, it seems like we can draw all this work together to describe the process of core formation as an actual a process by which things come into better equilibrium, which would mean that there's a kind of universal description of baryonic processes giving you a core. And that could give you a way to completely untangle what particle physics processes can do from what gravitational astrophysics interactions can do. But that's work for the future. So thank you very much indeed for listening.
So we've run a little long, but I think we'll take a couple of questions before we go to test cookies.
Well, actually, getting back to this issue of particle collisions. So earlier was sort of raising an issue that in principle, some surfaces they could make the halo more custom.
That means that things.
Negative specific heat. This is I kind of understand thermodynamics, but
yeah.
By the negative specific heat, then I could conduct energy out from the center and make it custom.
That is correct, yeah.
Mediated by the dark matter collisions, and yet in some intermediate regime, it looks like they're having the same effect as your potential fluctuations.
Yes, that's right.
So the maximum entropy is at fixed binding energy, basically? Or?
Yeah, so let's just untangle those two questions. So the first question about self-interacting dark matter, you're absolutely right. And so what the current literature seems to be claiming is that, yes, in the end, if you're allowed to move energy around arbitrarily, you do get this runaway instability where you form a very dense cusp and a big halo. But there is, as you say, some intermediate regime where you have a core. I haven't been involved in any of that, so I can't comment much more on that. In terms of the maximum entropy solution, the constraints that that's based on come from assuming all evolution is collisionless. So this conservation of the sum of the actions only applies in the collisionless case. So that will be violated if you have self-interacting dark matter. And so although on the face of it, it looks like they're getting similar density profiles, we may be able to put different bounds. I mean, for instance, I think you may be able to put a bound on how much energy can you inject into the dark matter population through purely gravitational interactions. It may be that it just stops soaking up more energy at some point because it's reached the most relaxed possible profile, if you like, whereas the self-interacting thing can carry on evolving beyond that. So this is all quite speculative at the moment, and it's hopefully in the next few months we'll be able to start firming it up.
Well, I would have thought that in the limit that you're maximally interacting, you just become a perfect gas again. And for that, we know the solution, because there, if you take the Lindenbell entropy, you just get a isothermal gas, where now the parameter becomes T, so beta is just T for the Maxwellian. But the second parameter, of course, is chemical potential. So you get K, you get T and mu, and that if you put a finite mu in, you also get a core, I believe, in a gas. I think that's right, so that's something you can check. So you can actually calculate by hand. the full family of maximally interacting read points. So.
Okay, yes, that's an interesting point that hadn't occurred to me. Yeah.
Okay, so I think in the interest of getting away, we'll head upstairs for cookies. If you want to ask any more questions, catch them then, or you can catch them later, either today or tomorrow.